Okay, we're going to pick up with part 2, where we're looking at actually radiographic intensifying screens and, of course, their relationship with X-ray film. Let's see. We've talked about, the mechanics of using intensifying screens, and the reason that they are important because the X-ray film is manufactured to be particularly sensitive to the light that's given off by the crystals of intensifying screens. One of the things I didn't really kind of talk about is what's the whole point? And because using intensifying screens is so much more efficient than radiation striking film directly, the radiation dose is considerably less. And remember, we talked about at the very beginning of the previous that I originally started out at about 100 mass at 70 kV or 75 kV when doing a KUB, and by the time, I rephrase that, if we went with no intensifying screens for a hand, we would talk about 100 mass, and then essentially went down to 2 mass. So we really, if you get right down to it, we essentially had an efficiency increase of about 98%, I guess. But here's the thing. You're talking about adding an additional layer in between essentially the image and the part, which is the intensifying screen. So one of the things that's going to happen as a result of that is there will be a small loss in resolution. And in general, you have to understand every time you add additional layers in here, that loss of resolution will occur. And it's no different here. Okay? Now, we've talked about this whole question of X-rays and film and things like that. If you have screen film that is manufactured, what really exposes it, of course, is going to be the light from the intensifying screens. And notice that really it kind of depends on the system you're working with. You could have, upwards of only a 1% interaction with the film. I mean, that's, like I said, incredibly inefficient. Okay? Because really what we're talking about then is utilizing something that gives you a far higher utilization, or more bang for the buck if you'd like. Okay? And if you get right down to it here, the screen crystals that are used, the screen phosphors, are much more efficient because you can see upwards to 60% of the X-rays strike screens that in turn interact, producing photons, light photons that in turn interact with the film. So you've got a huge difference between 1% versus upwards to 60%. Okay? Now, these intensifying screens and the piece of film are going to be contained in a reusable device that's called a cassette. Essentially, this is a stiff, structured mounting mechanism for these screens that is also light tight for the sake of the film. It is radiolucent insofar as it possibly can be, but that's what radio cassettes actually are. Okay, it's really, in a lot of respects, structurally, it's really no different from what you have with a CR cassette and all. But these cassettes that I'm referring to will have two or a pair of screens, one on one side, one on the other. Okay, they may be the same. There may be small differences between them, but the idea is to cause the emission of light that will expose the emulsion that's located on both sides of the film, hence the term double emulsion. Okay, here's a graphic that shows you what you actually have with all of this. This is the cassette right there, and as I said, this one here is a metallic cassette, and again, it's going to be it's stiff and it's going to be very light tight. Okay, you don't have a whole lot of wiggle room, I guess you say, in there. The piece of film is basically placed inside. Of course, what happens then is your intensifying screens are the cassette is built to match the size of the film. And then within the cassette, you have the intensifying screens. And in this particular case, we've got the two of them here. They may be slightly different. There may only be one screen. It kind of depends on the type of film you're doing. And obviously, it's like so many other things, it's the object of the game. Okay, The intensifying screen starts out with an active layer that contains phosphors. Now, phosphors are light emitters. Okay, we are looking at light emitters in this case that emit light when they are stimulated by X-rays. As a general rule, a phosphor will emit light when it is hit with something that has a higher wavelength. Okay, so in that respect, what you end up with is a lower wavelength structure. Now, there are different types of phosphors that are going to emit different wavelengths. Okay, they could be blue, they could be green. You've got all these different kinds of things out here. But the important thing to understand is phosphors emit light. That light there, again, is what really makes intensifying screens work. Okay, now, I mentioned this in the very, very first slide here, which is in the beginning, your intensifying screens that were exclusively used in a radiology department had a phosphor that was called calcium tungstate. When the radiation struck it, it emitted a blue light. Okay, now, it really wasn't a terrible match with light photons, but the bottom line was that it wasn't particularly efficient at converting X-rays into light. Okay, that's kind of the important point. So you'd put a lot of radiation in, and you'd only get a little bit of light. And if you wanted more light, you obviously had to put a lot more radiation in. That's what I mean about the question of efficiency. Okay. Then we got rare earth elements, which are frankly even used still today. Rare earth elements all have very similar atomic numbers. Okay, lanthanum, lanthanium. I always called it lanthium. It's not lanthium. Lanthanum, gadolinium oxysulfide are examples of rare earth phosphors that are used in intensifying screens. Now, Kodak, today is known as Carestream, are the ones that had Lanex cassettes. DuPont used to manufacture and market Chronex cassettes. They were based on different rare earth elements. Notice that the light was also different too. Here's the thing. You could not mix up a Kodak intensifying screen with a DuPont piece of film. It didn't work. Okay? Now, this is a little bit of what I'm talking about. We've got essentially three different types here. Now, calcium tungstate, they got tungsten here, but what they're referring to is calcium tungstate. So calcium tungstate. The amount of radiation, okay, as the energy of your X-ray beam went up, notice that it plummeted the attenuation. Okay, now we're talking about attenuation within the screens. Then all of a sudden you reached a certain level, which in KeV here, this is very high. This is not KVP. All of a sudden you had this huge spike, okay, in light emission by these screens. But the problem is this is the area here, okay, where we're working. This is the emission spectrum. We're in this area, okay? So you did not, you got light emission, but you did not have the most efficient in that case. So that's why I had to use 100 mass to do, for example, a KUB. Now, then you got lanthanum, and gadolinium. Okay, gadolinium you see here basically peaks at a point that is far closer to the range of energies that we typically use. Lanthanum, even more so. Okay, so logically speaking, the rare earth screens are a far better match, okay, for the types of energies that we use. In other words, you got the most bang for your buck, essentially, utilizing these cassettes as opposed to calcium tungstate. That means they were more efficient, the screens were at producing light, okay, based on the energy of the X-ray photons. Okay, now a couple of terms here. We're just pulling these essentially out of your book. The term luminescence is a material that gives off light, and, for example, a phosphor is capable of luminescence. Okay, now within that you kind of have subsets. Okay, fluorescence is what intensifying screens actually do. Okay, you irradiate an intensifying screen, it gives off light. If there is no radiation, nothing is happening. Okay, in essence, what's happened is sort of like a light switch if you have an incandescent light bulb, which is you turn it on, you have light, you turn it off, you have no light. There is also, though, phosphorescence, which is giving off light after a stimulus. Okay, a lot of things that glow in the dark, for example, and things like that, that's phosphorescence. Problem with this with intensifying screens is that means it's still giving off light even though there's no radiation striking the point. That means it's very error. I guess you'd say it's bad for screens because it's error driven. We call that afterglow or lag. Okay, now we've talked about speed, and remember, speed now is a function of the film screen kind of teamwork, I guess you would say. In this case now, we're looking at speed from the point of view of the screens, and in this case, we're looking at how well do the crystals, all right, in the intensifying screens absorb the radiation. How well do they take the radiation, the X-ray radiation that they've absorbed, and converted them into light, which we were just looking at here. We also want to look at how many of the phosphors are there, i.e. the thickness of the phosphor layer. Clearly, if the layer is thicker, there's going to be more crystals. At the same time, we're also looking at the size of the phosphor crystals. Remember now, size matters. Okay, small crystals will give you more resolution, okay, but less light. All right? So the speed of a system is driven by all of these things. Okay, so crystal size here, because this is the one here, I think I made a little bit of a muck-up here. The thing I want to point out is that if we're talking about the speed of the system, more crystals means a faster speed. Okay, if you have a thicker layer, you will have more crystals, ergo you will have a faster speed. On the other hand, where crystal size is concerned, smaller crystals will equal less light being emitted, so that the screen overall will have a slower speed. Let's stick with that. All right. Here, for example, if you look at the two of them here, what we have are crystals that are essentially the same size, but there is a thinner layer of them here. There is a thicker layer of them here. Okay? So you have, for all intents and purposes, fewer crystals here than you have over here to the right. If we click on the X-rays that stimulate the thin plate, you can see how there is light emitted, okay, overall. With a thicker plate, not surprisingly, you're going to have more light emitted, but notice also it's emitted over a larger area, okay? That also makes a difference because faster screens also affect the resolution of the system. Try this again. And you can see how you have the difference in the light. Okay, again, I want to point out, slower screens have smaller crystals, maybe even a thinner layer of crystals. That will give you better recorded detail, better resolution, okay, but at a slower speed. So which type of screens do you think would be most likely to be used with, for example, a wrist? Fast screens or slow screens? Okay. On the other hand, what type is most likely to be used on a lumbar spine? Fast screens, slow screens. All right, now we talked about this here. You're looking at the packing density here. This was just mentioned almost as an afterthought in your textbook, but I had this here, so I thought I'd put it on here. If you have a low density of screens here, only the individual crystal here is emitted, and you can see what happens here. It's now basically messing with the silver halide of the film emulsion. If you have a higher density, you're going to get more bang for your buck, and more is irradiated. Okay, so more light will go to work and affect the film more. All right, now the other thing that happened we talked about is that there are going to be light absorbing dyes in some cases within the screens. This is to ensure that only specific light is emitted, specific wavelengths of light is emitted by the phosphors. If you want strictly blue light, that means you do not want blue-green light, okay? It also means you don't want purple. You want blue. And that's what essentially is going on here. So if you have, for example, here, you have the distribution of light overall, and as you can see here, I guess you said the effect also on the film. This is the film down here. Okay, with dye, that light is absorbed, so you're only going to get basically a limited amount of light coming through that will record on the film. I'm sorry you can hear the kids screaming. That's what we listen to every afternoon. All right, now, increasing the speed, okay, means you can use less mass. Okay, this reduces the radiation dose to the patient. Now, quote unquote, typical speeds range from 100 speed, 200 speed, 400 speed, 800 speed. Okay, now, the faster the screens, remember that means you also have to use less radiation. There was a question on that packet that said 50 speed. Okay, that's kind of more of a mathematical exercise. It's not like we have very many, or ever had very many 50 speeds. Okay, it's relative speed, or RS, and what you kind of have to understand is that you're comparing one to another. And that's where the whole relative thing. It's sort of on the same idea as me saying longer scale of contrast. I'm comparing it to something. Shorter scale of contrast, not just short scale. Because it's always relative here. Okay? So if you are going to compare a 200 speed system to a 100 speed system, what you have to understand is the 100 speed system is only half as responsive, okay, as a 200 speed system. Okay? As a consequence, you're going to have to change your mass to reflect that. The 100 speed system is going to need twice as much. On the other hand, reverse it. If you're going from a 100 to a 200, you need to cut your mass in half. All right? Comparing it again, if you're going from a 400 speed down to a 100 speed, you have to recognize that the 400 speed system is 4 times as fast. So if you're going essentially you're going to have to change your mass. Okay, enough's enough. All right. Now, but please understand something. Again, there is always a downside. Okay. Yes, you're basically improving the radiation dose to the patient, or reducing it, but you're also having poorer and poorer detail because of the number of crystals, okay, and also the size of the crystals. All right, so here is the relative speed equation, mass divided by mass 2. Notice that this is inversely proportional. I always thought this is sort of different, okay? Please keep in mind, it looks structurally like what you would expect, for example, for grid ratios. It's not exactly quite the same thing, okay? So you've got an inverse proportional going here. So the old mass over the new mass equals the the new intensifying screen, speed over the old intensifying screen. Screen. Yeah. All right, here's an example. You're using 20 mass, all right? You're with a 400 speed system, okay? You're going to get that image. You've got to get it. Patience preggers, though. He's going, I have an 800 speed 14 by 17. So what does that mean in terms of what you're going to use for mass? Remember, the object of the game obviously is to reduce the radiation dose. Well, all right, you've got the old mass, okay, divided by the new mass. We don't know it. You've got the new screen speed divided by the old screen speed. All right, new being 800, old being 400. Do the math. That means that your new mass would be 10 mass, which essentially is 1/2 of what you started with here. Okay? So if you're going from 400 to an 800, you essentially have to cut the mass in half, which is kind of makes sense. All right? Here's another one. You work for a rheumatoid arthritis doctor, and he wants the best recorded detail possible. Okay? You've got a couple of alternatives there. Okay, you've got a film screen system that's a 200 speed. You've got another one that is a 100 speed. All right, you got a technique for the 200 speed system, but you want to try to get the best recorded details, so you opt to go with the 100 speed system. Take a look at the math. Again, 3, which is the old mass, divided by the new mass, which we don't know, equals the new, which is 100, divided by 2, which essentially means you've got 3 divided by x equals 1 divided by 2. X will equal 6. Okay? In essence, what's happened is you're going to double your mass to compensate for the change in the screen speed. All right, now, something else that needs to be pointed out about all this. As you use less and less radiation, all right, what happens is that you are going to get an incomplete exposure over the kind of the whole field. This is, of course, what we've talked about in digital as image noise. And, it's happening because you don't have enough radiation. Well, with film screen, it can happen, but it's most likely to happen at high-speed reverse screens because you literally find yourself using much less radiation. And in the digital world, they call this quantum model. But essentially, it's the exact same thing as image noise, okay? But the term quantum model is just simply associated with film, okay? All right, so it is possible to have quantum model in an analog system. Okay, now I talked a little bit about cassettes and did a measurable job. It's going to be a holder that contains both the intensifying screens and where you actually put the film. It is going to be light tight and it has a compression to ensure that you get really close contact with those screens, because if there's gaps there, then you're going to have blur. The other thing to keep in mind is that it is going to have a low absorption characteristics through the front, because you don't want the cassette absorbing the radiation. If it's absorbing the radiation, that's not helping the dose any. Okay, there may be a radiation absorbing material on the back of it. It won't be in the front. And the idea behind this is to absorb backscatter. Now, we've talked about backscatter. Okay, radiation passes all the way through the cassette and strikes the back of the cassette. It might strike the back of a stretcher or bed or whatever else it is that you've got out there. The scatter comes back and strikes the cassette and causes exposure. Okay? You want to prevent that, because whatever you're getting there, it is not the transmitted beam. So it will harm your image detail. Well, not detail so much, but it's going to fog things. All right. Now, we talked about spectral matching here again. All right. Again, I just want to point out, okay, the light that is emitted from the screens is unique. Film has to be manufactured to respond to it. If you have rare screens that emit light in a particular hue, okay, you have to have the film that actually does that too. Okay, I don't know what else to say about it. All right, so if you put the whole thing together, this is kind of what it looks like. You've got essentially the base, remember, which is the polyester, and the adhesive layers. Okay, and on either side of that, because this is going to be a double emulsion film, you've got your gelatin plus your silver halide crystals. Same thing going on over here. Okay, now this piece of film right here is placed inside of a cassette, okay, that is light tight and very kind of compresses the film so that you have perfect, or as perfect as you can get, contact between the intensifying screens, okay, and the film. You don't want any gap in between there. Now the radiation comes through, causes the phosphors that are located in the screens to emit light. So X-ray radiation causes the emission of light photons. Those light photons in turn will cause changes within the silver halide and produce these changes that I'm talking about. These chemical changes are not visible to the naked eye. Okay, what we call a latent image though occurs, and it will only appear following processing with wet chemicals. I think that's it. Okay, so we're done with this here. If you have any questions, we'll talk about it. All right, take care.